Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at networks, specifically their nodes and edges. So networks are basically just collections of these things called nodes or vertices. They mean the same thing. And the things connecting them called edges. So the nodes and edges can represent anything. There's heaps of areas in the real world in which they are used. So for example, each node could represent a city and each edge could represent a road that connects them. For something like this, which we'll see as a directed graph, it could model water flow. This could be like the source of water, like a lake or something. This could be different reservoirs. We'd call this the sink, whatever. Networks are also used in contact tracing to see who's infected who with an infectious disease like COVID. They're also used in mapping social networks. They're used in many different areas of mathematics. All we're really needing to get out of this video are some definitions. So let's look at this one here. So this is called a connected graph. Now note that network and graph can be used interchangeably. I know it's confusing that mathematicians often use different words to represent the same thing, but just note graphs and networks are the exact same thing. So the reason this graph here is connected is it's possible to go from any vertex or node to any other node. That, however, is not possible in this one. If you're at vertex G, for example, you can't get to some of the others. Because these edges have directions on them, if you're in vertex J, you can't get to any of the other vertices. So that's why this graph is unconnected, whereas this one was connected. So this one is an undirected graph. What that means is there's no direction, no arrow along the edges. It means that travel is possible in both directions. You can go from A to B or B to A. On the other hand, this is a directed graph because each edge has an arrow. You can only go in one direction along each edge. For example, you can only go F to I, not I to F. Now, sometimes you will see numbers on edges in a network. We call those weighted graphs. Each of these numbers is a weight, and they're very important. They could represent something like distance between towns. They could represent the cost of cabling, whatever. Sometimes they will have them, in which case they're weighted graphs. Sometimes there will be no numbers on the edges. They're unweighted graphs. So this here is a graph that has 1, 2, 3, 4 vertices or nodes. Remember, vertices and nodes are the same thing. It has 1, 2, 3, 4, 5 edges, whereas this directed graph over here, 1, 2, 3, 4, 5, 6 vertices or nodes, and it has 7, 1, 2, 3, 4, 5, 6, 7 edges. Now, a couple more definitions that are important. This graph here contains a loop. A loop is this thing here. It is an edge from a vertex to itself. It also contains what's known as a cycle. So a cycle is a path from, well, it can go through as many vertices as you like that starts and ends at the same vertex. So for example, we can start at B and go on a path through other vertices back to B. So this graph does not have any loops. It has no nodes that connect to themselves through an edge. It also has no cycles. So one other thing that is very important in definitions is this notion of the degree of a vertex. That'll become especially important when we look at Eulerian and Hamiltonian paths. So what do I mean by the degree of a vertex? Well, it's actually pretty simple. It's just how many edges connect to that node or vertex. So for example, if we look at this graph here, we have that the degree, so we'll just call it deg A, degree of A is 1. There is only one edge that connects to A, whereas you can see for something like D, its degree is actually 4. That probably sounds a bit counterintuitive, but there is 1, 2, and we count the loop as 2. Its degree is 4, so there are like 4 edges, or 4 ways you can get out of D. You can go this way, or this way, or this way. So the degree of vertices in a graph like this, a directed graph, is a bit more complicated. There's actually an in degree and an out degree, but we won't go through that in this video. Instead, let's look at solving a problem where we would use a network. So here I've come up with a table that shows the cost of travel from each of these suburbs to one of 5 suburbs. So let's go ahead and draw a diagram to represent this. So each of the 5 suburbs will be a node or a vertex. So let's start with L. So Lynham, we know, connects with Dixon, O'Connor and Watson. O'Connor and Dixon also connect to each other. So what we might do is put O here and D here. So they have a little cycle going on. Now of these, only O'Connor connects with the city. So I'll put it down here. Now Watson, on the other hand, connects with all of them. So I can put Watson over here. So we have our 5 vertices. Let's now draw the edges. So we know that Lynham connects to Dixon. It also connects to O'Connor. Now it might look hard to connect Lynham to Watson, but you can draw an edge like that. That's absolutely fine in a network. So let's put on the amounts. So Lynham to Dixon and Lynham to O'Connor are $3 each. Lynham to Watson is $5. Now let's look at Dixon. So Dixon connects to O'Connor, so we'll put that there, and that was $6. And of course Dixon connects to Watson for $2. Now we look at O'Connor. So O'Connor also connects to the city for $4 and $3 to Watson. And now we connect Watson to the city for $1. So the kind of question you might be asked is, what is the cheapest way to go from Lynham to the city? So there are lots of different paths we can take here. We're going to look more formally at how to do this in subsequent lessons, but for now we're just getting used to the idea of weighted graphs. So there are lots of different paths I could take. I could go Lynham, O'Connor, city, that would be $7. I could go Lynham, Dixon, O'Connor, the city, well that's going to be pretty expensive. Hopefully, eventually we can see that the cheapest way is to go from Lynham to Watson for $5 to the city for $1. $6 is the cheapest. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.